last time we introduced two main types of renewable energy, which are no, we just introduced as renewable energy. Uh, we did last time. So today we will do wind power. Can you remind me what did we do last time? Hydropower. Okay.
Yes,
So yes,
we did
as
closing.
renewable we have seen hydropower, and as non-renewable we have seen fossil fuels. And today we will introduce a new type of renewable energy, which is wind power. Okay. So we have several drives that shift the world to use renewable energy technologies such as wind power, solar power, nuclear power, hydropower, and biomass. These drives are first, you have the high cost of fossil fuels and their availability. They are not a lot of available in current times because we have seen last time that the reserves are reduced with time and we are close from reaching a crisis on this level. In addition to the economical crisis, so sometimes we have very high cost of oil. This is why we should start to switch for other techniques as renewable energy. And a second cause, which is very important for the environment, is the global warming effect. So we need to reduce the greenhouse gas emissions in order to avoid the excess of rise of temperature. And finally, the third cause is the need for energy diversity and security. Okay, so using renewable energy is one of the most secure issues because, in general, it's free and it is widely available. So it's renewable, so we can always have it. So no, we don't have a risk in if you want in one day and it will finish. Plus, uh, it has a good impact on the environment. It does not harm the environment. We will see in this chapter in particular that wind power is one of the most important renewable energy, and if we use it appropriately, we can cover a lot of needs. So the original source of wind is radiation from the sun. You know why radiation of the sun will play a role in wind creation? Who has an idea? How can solar
because
radiation?
of convection.
Yes, very
Uh,
good. It's very similar to what we have introduced in chapter 2. You remember in chapter 2 when we defined convection, we said that convection can be due to what? Density difference in a fluid, yes? So mainly when you have a density difference, what will happen? The heated particles will move up and the cold particle will replace them. Okay? So here what will happen is that at the local level, solar energy will be absorbed in a different way by land and water, which will result in convection currents and pressure winds. Minor fluctuations to the global wind pattern are set by the position and rotation of the Earth with respect to the Sun. So, for example, so this is at the local level. So, if you consider a certain space and you have that it's heated in a different way, so you will have zones with higher temperatures than others, and due to difference in temperature, this will create difference in density, and difference in density can create motion of the fluid. This will create wind. So, this is at a micro scale, if you want. Now, at a macro scale, at the global level, we have that a higher intensity solar flux will hit the equator level, which will cause this warmer air to rise up. And this will leave low pressure areas behind from the equator. This is why cooler air will flow from the north and the south towards the equator. So, in this way, we will have convective currents first from the equator towards north and south, and then to fill the gap in the equator because this will create low pressure at the equator level. Then air will flow from north and south towards the equator. And this cycle will be repeated, which will create convective current over the whole planet. Now, It is estimated that 0.5% of the incident solar power, which is 1.35 kilowatt per meter square. If you remember, we have derived together this constant in chapter 2. Okay, so 0.5% of this amount will be converted into wind. It's true that 0.5% might seem small, but because the solar power is very, very high, so if you take 0.5% of 1.37 kilowatt per meter square, it will lead to 7 watt per meter square, which is very high. So in fact, this will need to a power of 10 to the power 15 watt if you consider the total area of the earth. And 10 to the power 15 watt is 100 times higher than the global power use. So if we can extract a certain in enough amount of wind energy, we can use it to cover all what we need. So this is why it's very important to benefit from the available wind energy. Okay. Now, wind has been used a lot in history, and first it was used for trading. So, for example, as you can see here, for transportation issues, as in boats. Then, after an industrial application, it was used to pump water and for grinding purposes. And finally, in the 20th and 21st century, the main application were generation of electricity. So as you can see, wind can be used to produce several type of power. Now, the global installed capacity has grown a lot with time. Okay, so for example, it is growing at nearly 30% per year since 2000, reaching 336 gigawatt in 2014 and providing 735 terawatt hour of electricity, which is a very high amount. And this represents 4% of world electricity energy consumption. But this percentage is still increasing, and it is projected to produce 10 to 20% of the total world electricity consumption by 2050, which will save a great amount of fossil fuel resources and greenhouse gas emissions. So current wind turbines are very powerful, and the technology in this field has led to an increase of power 100 times more than the one used in the 18th century. So the development of wind turbines was very significant. For example, we have in Spain, 16% of electricity demand is supplied by wind farms. In Denmark, 33% is supplied by wind farms. So as you can see, in several countries of Europe, wind energy is widely used. So from here, if we look at the percentage of increase with per year of wind energy use, we can see that this type of energy has a very important future. With annual growth rates of nearly 30%, wind could generate 20% of the national electricity by 2020. And here we can see, for example, the percentage in blue, the percentage of wind compared to the others. So you can see that with time, this percentage is increasing and consists of an important fraction of energy supplied. So here it's a numerical example showing the use of wind energy worldwide. So for instance, at the end of 2007, we have, let's say, 93,823 megawatt produced of electricity produced by wind energy. While in just after 1 year, okay, so in 2008, the total was 120,000, okay, times plus 791. So nearly the increase you have 27,000 1,000 new megawatts of energy from wind only in 1 year. So you can see the large increase. Now, a lot of countries are relying on wind energy more and more, and particularly the developed countries, because they are developing new technologies to enhance the performance of wind turbines, as we will see in this chapter. So, for example, one of the main countries using wind energy is the US, Germany, Spain, China, Italy. So you have a lot of countries, mainly in the not only in Europe but also in the United States of America, and also in you have the China, which is a very it's a developed country also. So you can see here that the most important countries are relying a lot on wind energy. In this graph, we can see how the world wind energy capacity was increased with time. So we represent the variation of gigawatts of installed capacity with years, and you can see it's like an exponential increase. So you have the rate of increase is very high as we advance in time. And the cause of this is that wind power presents several advantages. So first, it's a clean source of power. It does not lead to emissions. No fuel is needed. It is a flexible technique because we can, in general, wind is widely available. It has a large potential for growth, especially with the development in technologies. And it is economically viable because most of the time we have wind available. And one of the most important advantages is that the benefits of wind power to environment, because it will not lead to air pollution. We don't have greenhouse gas emission. We don't have any emissions of different than greenhouse gases as mercury, which can pollute water. So we don't need treatment of air and we don't need treatment of water. Now, we have one disadvantage, which is that wind turbines in general kill birds. But if we compare killing birds by wind turbine compared to other human activities, it's not a very high percentage. Okay, so the estimate is nearly 1 to 2 bird deaths per turbine per year. So it's still acceptable. And since global warming is the single biggest threat to wildlife today, then we can consider that this is a small disadvantage of wind turbine compared to other technologies as using fossil fuels. And a recent study in Nature found that more than 1/3 of species worldwide will be reduced a lot or will not be present anymore by 2050 if global warming trends continue. Now, other limitations of wind power is that the power density is very low. So if we put just one wind turbine, it will not produce a high amount of power. This is why we need a very large number of windmills to produce modest amounts of power. So this will require a large area to put wind turbines. And another issue is the environmental cost. We have the material and maintenance cost of these wind turbines. In addition, wind turbines produce noise. So in general, we don't recommend to have wind turbines close to population. So they should be far from population to avoid noise. And plus that sometimes they say no, they have a bad visual impact. Their appearance is not very nice. So in order to avoid the bad impact concerning noise, what we can do first, we are trying to with modern turbines to reduce the noise effect, okay, by using advanced technologies. Plus, noise can be reduced with setback distance. So we use wind turbines farms far from population. So utility scale wind turbines should be at least 1/4 to 1/2 mile away from residence. And also concerning another disadvantage, some people may complain that wind turbines look industrial and take away from the natural beauty of the landscape. But of course, this disadvantage is not very important compared to harming the environment and leading increasing global warming effects. Now, how to generate electricity using wind power? The concept is very simple. You have that, for example, this is a wind turbine. Okay, it has an axis. In general, we use wind turbine with horizontal axis. So this is the axis. You have three blades. Okay, you can have four blades. You can have two blades. You can have three, four, but the widely used one is three blades. So what will happen is first the blades will catch the wind and spin. So under the effect of wind motion, the kinetic energy of wind will be transformed into a rotational energy of the blades. Then this rotational energy will be converted into electrical energy through generators. And generators will be related by cables that will carry electricity to transmission line. Now, to optimize the performance of the wind turbine, we assist it by a computer system that will control the direction of the blades, because depending on the wind direction, to profit to the maximum from the direction of wind in order to induce the rotational effect, we need to position the blades in a way to be, if you want, perpendicular to the wind hitting the blades. In this way, this will lead to maximal rotational efficiency. Okay, and the power produced will be equal to the voltage times the current. Okay, so now here we can see the different components of a wind turbine. A nacelle is a cover housing that houses all of the generating components in the wind turbine, including the generator, gearbox, drivetrain, and brake assembly. You have plus, of course, the blades and the axis of the turbine, and we have that the blade area is the area that is swept by the blades when we have rotation of the axis of the blades of the turbine. The rotor diameter is defined as the diameter of this circular area. We have the tower, which will relate the axis of the turbine to the foundation. And the hub height is defined as the elevation from the ground level to the axis of the turbine. Now, mechanically, how wind turbine will work, they will rely on forces of the wind on the blades, okay? And only two forces act on the wind turbine rotor blades, which are lift and drag force. The net of these two forces will induce a torque that will make the blades rotate. The vast majority of modern wind turbines are horizontal axis wind turbine, and their symbol is HAWT. Now, blades are like airfoils, like wings of airplanes. Okay, so due to the lift, these blades will rotate because lift forces will drive the turbine, as we will see in the next slide. So if you look at this figure, the mechanism of operation of a wind turbine is very similar to the mechanism taking place over the wing of an airplane. So this is the form of the blades is like an airfoil, okay? And it's not a symmetrical airfoil. Why? Because if you, in fluid mechanics, if you study flow over an airfoil, if it's symmetrical, then when the flow pass over this airfoil, the net lift force is zero. So there will not be a net force on the airfoil upward. However, if you have a non-symmetrical airfoil, or if you have a certain inclination of the airfoil, okay, what will happen is that, as you can see here, due to the flow over the airfoil, you will have below the airfoil a certain zone of low pressure, okay, while above the airfoil the pressure is higher. So in this way, the airfoil, which is like the aircraft wings and turbine blades, will affect the velocity of the air flowing, which will result in a force exerted by the airfoil on air to be directed downward. And from the Newton's third law, by action reaction, air will exert an upward lift force on the wing. Now, the angle of attack is defined as the angle between the chord line of an airfoil. So this is the line of the airfoil, this one. Okay, this is called the chord line. This is the flow direction, which is horizontal. The angle between them is called angle of attack. Okay, so with variable angle of attack, we can affect the lift force acting on the airfoil. This is why, in general, when doing the design, we can play with the angle of attack to see how it will affect the lift force acting on the airfoil. So the airfoil shape and angle of attack will work together so that the airfoil will exert a downward force on the air as it flows past for aircraft wings, and in this way, by action reaction, air will create an upward lift force on the wing. So here you can see this is your blades in form of an airfoil. You have the lift force is perpendicular to the airfoil, while the drag force is along the airfoil. And you know that to produce a torque, you need to have a force that is perpendicular to the arm. So it's mainly the lift force that will induce the rotation of the wind turbines. Now, we will just go over a small calculation to understand more how the wind turbine operates. So the dynamic pressure represents the energy per unit volume of the fluid. If you remember, when we wrote the Bernoulli equation, we had three types of energy. We have the flow energy, we have the kinetic energy, and we have the potential energy. Okay? The flow energy is related to the velocity of air, and it's defined as half rho u square. Okay, now if we have, so if you want the unit of 1/2 over rho u square is energy per unit volume. Okay, so the unit of the flow energy, half rho u square, which is related to the kinetic energy of the flow, is related to its energy over volume. Okay, so joule per meter cube. This is its unit. So for a fluid flowing with a velocity u across a cross-sectional area A, the volumetric flow rate can be calculated as V times A. So this is what we call Q, volumetric flow rate, Q dot. Okay, why we are introducing these concepts? Because if you want to calculate the power delivered by a fluid moving at a velocity u, so if you want to power, what is the unit of power? The unit of power is watt, which is equal to joule per second. So if you look here at your units, half rho u square is joule per meter cube. And if I want to obtain a power, which unit is joule per second, I can multiply the dynamic pressure, which is half rho u square, by the q dot. Because what is the unit of q dot? Q dot is in meter cube per second. Okay, and The dynamic pressure, which is half rho u squared, represents the energy of the fluid per unit volume. Okay, so if you multiply half rho u squared by q dot, which is in meter cube per second, you will get the power that you can extract from a fluid moving through a cross-sectional area A at a velocity u. Okay, so we can deduce that if we have a flow moving at velocity u through a cross-sectional area A, the power available is for this fluid is half rho A u cubed.